let's start, okay? So thanks for coming today. Makeup class. So let me just say what I'm going to do today. Okay, so I'm going to spend quite some time trying to do a better job than I did last time. Because last class, if I have u, condition on u, x, y, z, the probability of the conditional probability of w, okay, w is this one, condition on all these variables has to be equal to or is equal to pw condition on x, y. Okay? Okay? Right? So the idea is once I give you x, y, I can determine the conditional probability of this one. So once conditional x, y, the other things are no longer useful. Okay? No longer useful. So this is a very simple idea, right? Essentially what it says is the parent determining the children, right? So if I give you the information on the parent, and we're done. Okay, we're done. All right, so given the x, y, as long as I give you x, y, then we don't need information on u. We don't need information on z. In other words, this w will be independent of u and z. Okay, u and z independent as long as we give you information on x, y, conditional on x, y. X, y, it's independent of all the others. The parents fully specify the children. All right. Okay. So that's the first thing. The second thing we talk about d-separation. D-separation means independent. D-separation implies independence. And if they're not d-separated, if they're deconnected, then they're correlated, right? So what is d-separation? Well, let's think about x and y, right? D-separation means there are no open path. Okay, there's no open path between the two. So x to y, there's a path. Is it open now? Yes, it is open. So this is open path. So as long as there's open path, x, y are correlated. They're not independent. Is this an open path? No, it's not an open path. Okay. So how do I so first of all, x and y are correlated. They're not independent. If I condition on w, if I condition on u, is x and y, are they independent if I condition on u? Are they? If I condition on u, are they independent? The answer should be yes, because this path is blocked. Why? Because it's a collider, right? It's a collider. Okay. What if I condition on w? Are they correlated or independent? They are correlated. But what if I do this? What if I do u and w? So I condition on u or condition on w? Independent or correlated? Correlated. Very good. Because if I condition on u, I block this path. But if I condition on a collider, it opens the path, right? It was blocked, then it's open. So it becomes correlated. Very nice. What about u, condition on u, but also condition on z. Now this actually we haven't talked about in our class yet. But it turns out that if this path is blocked, there's a collider. It turns out you don't need to condition on a collider. If you condition on the children, it also opens up the path. Okay? Because look, intuitively it's easy to understand because w leads to z. If you fix z, you somehow you fix a little bit above w, right? So you introduce correlation here. Okay. So if I condition on z, also you will make them correlated. Okay, correlated. Very good. So that's the first thing I want to talk about today, right? Now let's go back to previously to. Okay, yeah, let's take a look at this one. So we'll be jumping around today, all right? Jumping around a little bit. Okay, let's focus on this picture, okay? A, B, C, D. What is the joint distribution of A, B, C, D? How can we write it? The joint distribution of A, B, C, D if we have this graph, what is the joint distribution look like? Well, I can say that first of all, people can see this graph, right? So for the distribution of D, by the way, I can always write it. I can always write it as, ABCD can always be written, decomposed into PD conditional A. So without looking at the graph, okay? No graph, just this distribution, I can always write it as PD given ABC. PC given AB, PA given B, and PB. Do people see that? Okay, I can always write it this way, right? This time this is PAB, PABC, PABCD, okay? Right, okay, this way. I can always write it this way. But according to this graph, right, what is PD given ABC? Remember the Bayesian network sort of property. PD given ABC would just be equal to, do people have an answer? Can I simplify this? It is just equal to PD given C. Very good, right? Okay? Because C is the only parent. So using the Bayesian network property, I can forget about AB. Given C, that's enough, okay? C is enough, C is the parent. So PD ABC is just PD given C. Now, what about PC given AB? Well, it's just PC given AB, right? But what about PA given B? It is just equal to PA, because why? Because A and B are independent, right? So they are no, it's not B is, sorry, I shouldn't say, yeah, they're independent anyway. So P given B is PA, right? So this is PB. So in the end, I can write PD given C, PC given AB, PA, PB. Isn't this obvious from the graph, right? I mean, the joint distribution was just PA, PB, PC given AB, and then PD given C, okay? It's very simple, right? You can write the joint distribution. Okay, now, what I'm going to say is, what if I do the experiment? Or what if I, so instead of having, so imagine that this is the graph that describes data from observational study. Now I'm going to do some experiment. Okay? I'm going to do C. I'm going to manipulate C myself. So as an experimenter, I'm going to come in and I'm going to set C equal to 1, for example. Okay? And so my question is, what happens when I do C equal to 1? So I go in, I set C equal to 1. Remember, actually said so we described this scenario last time, previously, I think 2 classes before. If I do C equal to 1, in terms of graph, right? After I do C equal to 1, so after I go in and set C equal to 1, how do we use the graph to represent the resulting data that I observe? Well, because now C is determined, if I do C equal to 1, then C is no longer determined by A and B. It is determined by me, right? So me is not in this graph. Okay, I could have A, B, C, D. So C only leads to D, so that's the same. But A and B no longer leads to C. I can say something like me leads to C, but that's unnecessary. Okay. So the result of doing experiment, or the result of do something, is to cut off the link, right? Cut off the link. So A, B, C to D. Okay. So so how do we write out the joint distribution? What is So now my question is, what is P, A, B, C? Let me see what I'm interested in doing. Right. So so what is A, B, C, D? The joint distribution of all of them, conditional on do C equal to 1. Okay. So I manipulate C. I go in and I set C equal to 1. What is the joint distribution of ABC afterwards? What is that? Okay. Now, here, it turns out that the result, we can write it this way. Because the way to think about it is before we have A, B, C, D. Okay, just before do A, B, C, do C equal to 1, we have joint distribution A, P, A, B, C. Now, using the graph structure. Now, first of all, okay, before we do any manipulation, the original one. Okay, so this one. For this one, what is P, A, B, C? Well, I can always write it. I can always write this as PA conditional on the parents, PA, parents of A. In this case, there's no parent. PB conditional on the parents of B. PC conditional on the parents of C. PD conditional on the parents of D. I can always write it this way, right? But it's the same as the one I just wrote before, where PA just PA, PA given parents A just PA, PB given parents B just PB, PC given parents C is PC conditional. This one is equal to PC conditional on A and B. Okay, parents of C, and the PD given parents A is PD conditional on C. Right? Okay. All right. Now, what is the result of, what is this? What is the result of do C equal to 1? What is that? P, A, B, C, D given do C equal to 1. Now what is that one? Okay. Well, the effect of do C equal to 1 is to break the link of any parent to C. So C no longer has parent, because C's parent is me now. Okay, I'm the experimenter. I go in and do it. So there's no longer a parent for C. So PC given parent A, PC given parent C, but we still have this one, right? But PC given parent C becomes what? Becomes just PC. Okay, right? And in fact, it is not just PC, but it's PC equal to 1, right? Because I do C equal to 1. Okay? So C is 1. C is fixed to 1. So now, we can write a PA given PAA, PB given PAB, okay? But then, for this one, it is, we no longer, well actually, so this, because C no longer has parents, so this become just the PC, but then it's actually not PC because I fixed C to be 1, right? I actually fixed C to be 1. So this entire thing is actually gone. The entire thing is gone. Nothing. There's PD given PAD, right? Okay, that's it. Okay. Now, but there's another way to write it, which is I can write it this way. I can write P A B C D given do C equal to 1. I can write it this way. I can write P, still the original, okay, the original one, CD, but C now is equal to 1 because I fixed it to 1, divided by P C equal to 1 given PA C. Okay, so basically what I'm saying is I'm deleting this part, okay? Right? So I take the original distribution and delete this part, right? Whatever is left is my new distribution after I do this distribution. Right? Now the only difference, now it's actually not exactly as simple as just deleting this part. Why? Because look, what is PD given PAD? What is PAD? PD is C, right? But it's just not C because now I fix C equal to 1. So it's actually PD given C equal to 1 because I fix C equal to 1 now, right? So that's why the fully correct way of writing it is PAD given C equal to 1. So everything is C equal to 1. So not C equal to 1 everywhere. But then divided by this thing because this is we don't want this. It's divided. So that's the way to write it. Alright? But what is this thing? Bear with me because we're almost there. What is this? Okay. Well, it turns out mathematically this is just equal to P A B let's see, conditional equal to 1, but I don't need it anymore. B conditional on C equal to 1 and PAC times the probability. So this is a probability, right? Probability is essentially equal to this expression. Equal to how, why is it equal to this expression? Because, look, because what is this? This is C equal to 1, PAC divided by PAC, right? Sorry, P, okay? It's probability. Okay, right? So this is go up, this part at the top, so that's why we have a PPAC here. And then this thing divided by this is conditional on C equal to 1. Okay? So basically we have PAB conditional on C equal to 1, PAC times probability. Right. So this is our main result. Okay? So this is saying that if I give you a joint distribution ABC, and I zoom C equal to 1, okay? So I go in and I set C equal to 1. How does this mean change the joint? Right? How does an experiment, or how does things like this change the joint distribution? Well, easy enough. The joint distribution becomes this new thing, which is A, B, B, conditional on C equal to 1, PAC, and probability. So in other words, what is this? This is the causal effect, right? Now think about this object. The causal inference from this perspective is not difficult at all. Because look, this is, what is this? This is the causal effect of C equal to 1 on the joint distribution. Right? So if we zoom C equal to 1, and you know, how does it change the joint distribution? So this is literally the causal effect of C equal to 1 on the joint distribution. Right? Now, what can be the causal effect is very hard to get. Because the causal effect is not equal to linear equal to PABB given C equal to 1. It may not equal to this one because this is correlation, right? This is correlation. This is correlation because correlation is a zero, right? But hey, it's not that difficult because yes, it's not equal to this, but it's actually equal to this. Okay? It's actually equal to PABD. It's not equal to PABD conditional on C equal to 1. So it's actually equal to PABD conditional on C equal to 1, but also conditional on the parameter. And then times the probability and the joint distribution on the parameter. And then that gives us the probability. So, right? So, to get this probability back, you know, in order to get this probability back, all I need to do is to get this and this. So, do you see this from there? Do you see this from there? In other words, if I tell you that I have A, B, C, D, okay? The original before experiment. Okay, before experiment is observational data. I tell you that, you know, the C, A, B, C, D, C, D, and C, everything, okay? All the values are in the observation. Without this, can we get a causal effect of okay, you can get this part from observational data. This is simply the probability of ABB condition on C equal to 1 and parametric. And the parametric is AB, okay? So you can get it, right? What is in this case, what is the parametric? Parametric is AB, right? So this part simply becomes PABB conditional on C equal to 1 AB. But once you conditional on AB no longer needed, right? So we don't have this anymore. So this is simply become PD given C equal to 1 AB. Okay? Now, what is this part? What is P parentheses of C? Parentheses A and B. So PAB is simply PA PB. Okay, right? So if we observe A, B, C, D, if we observe all these 4 variables in the observational data, then can I use the observational data to estimate this part? Can I use observational data to estimate PD conditional A is equal to IB? Of course, right? Just look at the observation data, right? Just look at the distribution of D when C equal to 1 and the conditional value of AB. So we can get this from observational data. Can we get this from observational data? Of course, okay? Can we get this? Of course. So we have everything. So I just so you in this case, you can get your causal effect from observational data directly. No need to do experiments. Okay? No need to do any experiments. You can directly get it. All right. It's very simple. Okay. Now you say, okay, if it's that simple, why do we say causal inference is hard? Causal inference is hard because in reality, we often do not observe A or B or C or D. Okay. So in reality, we want to know the causal effect of C. We often either do not observe A or do not observe D or do not observe B. If we do not observe any of them, so suppose we do not observe A and B, then in reality, can I do this? No, I cannot do this. Then it becomes hard, okay? But if we observe everything, just use this formula, okay? Just use this adjustment formula. Sometimes this is called intervention adjustment formula, right? Or whatever you want to call it. But the idea is if you observe everything, then just use this simple adjustment formula, right? And you can get the causal effect. Okay? You can get the causal effect. Now, this is the causal effect of C on the joint distribution. What if I'm interested in the causal effect of C on a particular variable? Okay, so I just want to know the causal effect of C on D. Okay, right? I just want to know causal effect C on D. So, what I want to know is PD conditional on do C equal to 1. All right. Actually, let me see. Now, in this case, it's not that interesting because PD given do C equal to 1 is actually, if you can directly tell from the graph, it's actually just equal to PD given C equal to 1. Right? So because from this graph, it's not that interesting. It's directly this one. But let me just say. Let's just be a little bit general. Let me see. Let me change it to. Yeah, let's do this. Let's suppose I have this kind of graph. A goes to C, B goes to C, C goes to D, but also A goes to D. Okay, I'm going to do this. Now, in this case, first of all, what is the joint distribution? Or let me just say, okay, I want to know probability of D given, okay, do C equal to 1. Now in this case, this is no longer equal to PD given C equal to 1. Okay, it's no longer equal to that. Why? Because are people clear why they're not equal? Because C has a direct causal effect on D, but then there is an open path, right? There's an open path. That there's also a backdoor, but we'll talk about that later. But there's an open path that induces a correlation. So the correlation between C and D no longer indicates the causal effect, right? Okay. So what is it? What is this thing then? Well, it's very easy. Use our formula, okay? The formula is the PD given do C equal to 1 will be equal to PD C equal to 1 conditional on the parent of C and the P parent of C. That's the one we just used. The only difference is just now we're talking about joint distribution. Right now we only have one variable. Do people see that? Okay, previously we have P, A, B, C, D, right? A, B, C, D. What is A, B, C, D on do C equal to 1? What is that? That's simply P, A, B, C, D conditional on C equal to 1, but also conditional on the parent of C, and times the joint distribution of the parent of C, right? So this is our previous result. So all I'm doing here is to replace the joint distribution, like the joint distribution of ABCD, with a single variable D. Everything else is the same, okay? Everything else. So this formula is still holds, okay? Still holds. So in order to know the do C equal to 1, in order to know the causal effect of C on D, all we need to do is to change it into this formula, where it's the distribution of D, conditional distribution of D, conditional on C equal to 1, but not only conditional on C equal to 1, but also conditional on all the C, the parents of C, and then times the joint distribution of parents. And that will give you the causal effect. Okay? That will give you a causal effect. Okay. So what is this? Like what is this thing? Can we write it out? This would be from this graph. Okay, from this graph, it's P, D, conditional on C equal to 1. But what is the parents of A, C? A and B, right? Okay, very good. Now, PD, but PD, using this graph, all right? D, these parents are, who are these parents? C and A. B is not the parent, right? So PD given CAB is equal to PD given CA. We don't need B, right? Clear? Okay. So it's just PD given C equal to 1A, and times the parents of C, right? The parents of C will be PA, PB. Okay, PA, PB. But since B is no longer controlled here, we no longer need B. Okay, we no longer need B. Because PD given C equal to A, right? But look at what is this one? So what this formula tell me is that in order to get the causal effect of a C1 equal to D, in order to get the causal effect of C on D, we only need to estimate, we only need to get this thing and this thing. So this can be get from data, right? And this can also be observed from data if we see A, right? If we see A. We assume we always observe C and D because that's what we're interested in, right? If we observe A, then we can get this one. But what is this? What is PD conditional on C equal to 1A? This is simply look at the correlation of D and C while condition on A, right? Which is what? Which is blocking this path, right? So that's what we're doing, okay? We're estimating this. We're exactly using the strategy that we talked about earlier, which is in order to get the causal effect, we need to block this path. When we block this path, whatever is left, causal effect, okay? Causal effect. And that's what we're doing. Okay? This is it. Right. So we get this. Just make a simple adjustment and we get this. It's a pretty simple idea, okay? It's a very simple idea. All right. So what it's saying here is once we control, so if we want to know the causal effect of something, then in graph terms, right, we just need to control for all the parents. Control for all the parents of the treatment. And we're done. Okay, we're done. And just using this adjustment formula, we're done. So let's go back to the first case. So that brings us to the formula. Actually, this is what I described earlier. Hold on, let me see. Actually, not this one. Okay. So this is the formula we actually discussed last time, but I didn't really spend time to derive all this. But so this is a general formula we can always use, which is in order to see the causal effect do XA on Y, all we need to do is to write it in terms of this formula, where It's y conditional on x equal to a, right? And control for the parents of x. Just control for all the parents of x, because the parents of the treatment. And times the joint distribution, probability of time dependence. Right? And the only thing here is that we, because the parents of x can take on many values, so we integrate with respect to them. But that's the same thing as we just talked about, okay? The formula. So the causal effect of x on y is y conditional x and conditional parents of x, and times the joint distribution of the parents of x. And just integrate over all the values, and that's it. Okay? So this is the way to calculate the causal effect. Now, let's try the example, okay? Very simple example. So this example from the fumigation yield. Okay, right? F means whether we use fumigants. E means the worm. Okay, how many worms there are. Y is the crop output. So how do fumigation influence output? Well, fumigation controls worm, and a worm has the effect of output. The weather will affect output. The weather will also influence whether farmers want to use fumigation or not. If it's raining, they don't want to go out. Okay, so that's the weather influences fumigation. And then finally, the cost influence fumigation. If it's expensive, then they don't want to buy it, so they don't use it. So cost influence fumigation. The cost will influence both the cost and the yield will influence the final price of the crop. The final price of the crop. If we produce a lot, price is low because supply curve goes this way, right? If the cost is high, supply curve goes this way, and the price is high. So that's our causal graph of what's happening between fumigation, the use of fumigation, and the crop output. All right. So now I'm interested in the causal effect of F on Y. Okay, the causal effect of F on Y. F is a binary. Use fumigation or do not use fumigation. Okay, equal to 1 or 0. So I want to know the causal effect of fumigation on output. How do I do it? First of all, can I directly, is the correlation between F and the Y the causation? Well, is it? It's not, because what? Because which path is open? Is this an open path? Is this an open path? Is this an open path? Yes, but that's what we want, right? But is this an open path? No, because here's a collider, okay? Here's a collider, it's blocked. Is this open path? Yes, okay, yes. All right, so this is the open path we need to control. But anyway, so we cannot directly see the correlation, okay? We have to do some adjustment. What adjustment do we need to do? Let's use this formula, all right? So the adjustment we need to do, or let's just say so instead of P, let me use expectation. Okay, suppose we're not interested in the population or probability distribution. Suppose let me still use P. I'm sorry, because I write it in my slides. So the probability of yield conditioning on do F equal to 1, use fumigation on the crop, will be, according to this graph, will be equal to, remember the formula. The formula is the probability of y conditional F equal to 1, but then I need to control for all the parents. So the parents of F is W and C. Okay, let's see. Let's condition on them. Okay, so for example, W equal to small w, C equal to small c, right? Just condition on the value, fix their value. C and the W are the parents. Okay, times the joint distribution of W equal to W and C equal to C. Okay? So W can be, now, so this little W is just a value of W, okay? It can be anything. The C is a little value, so it can be anything. And then, of course I can, because these can be many things, so I need to add up all the little W, little C, okay? So just sum over all the possible values of the parents. Right? Sum over. And that's it, okay? So this will be, so they are equal. Okay. Now, right? So this is the formula. This is the formula we have. Can I estimate this from data? Can I estimate this from data? Can I do that? if I observe weather, and if I observe the cost, then I can estimate this from data, right? If I observe weather, I observe cost, I observe crop output, of course, yield, I observe yield, and then of course fumigation, etc. So all I'm saying is, without doing experiments, just take the observational data. In the observational data, I have all the data about whether they use fumigation, what the yield is, or weather is, what cost is. If I have all this information, then I can get this from data, and I can get this from data, and I can calculate this, right? So then we are done, right? We're done. So immediately I can get this causal effect by using this simple formula. And this simple formula, the idea behind the simple formula is very easy again, okay? It's a very easy, simple idea, which is we need to control, we need to turn this do notation into a simple conditioning, but also condition on the parents. Okay? Also condition on parents times the joint distribution of parents, and that's it. Okay? That's it. Okay. Now, I can replace the probability P with an expectation, right? So if all we, if all we care about is the expected yield, right? If all we care about is the expected yield, if we do f equal to 1, then everything becomes expectation here, all right? So this is still P, all right? This is still P, but this becomes expectation. So the way to estimate this causal effect, expectation, is to estimate this and estimate this. So far what have I done? I have made the identification argument. So remember, causal inference is two-stage. The first stage is identification. The second stage is estimation. So far, when I'm doing all this, I haven't done any estimation. What is estimation? Estimation is to give you a model, and then you estimate the parameters, right? Estimate the parameters, or you learn the model. Am I doing any estimation here? I'm not doing any estimation. I'm just doing identification. What do I mean by identification? I'm showing you that if we observe all these values, if we observe W, C, F, Y, then I'm showing you that we have a unique way of computing the causal effect. So in other words, if all I'm showing you here is if we observe all the variables, W, C, F, Y, we can uniquely compute, or it uniquely determines the causal effect of interest. And that is called identification. Okay? So now let me ask you, if I observe W, C, F, Y, but if I only observe like 2 data points, okay? So W1, C1, F1, Y1, W2, C2, F2, Y2. Can you get this causal effect? Probably not, right? Only 2 data points. You're not going to be able to do anything, okay? Because from 2 data points, you cannot get the distribution, you cannot get the expectation, right? So the identification argument doesn't care how many data points there are. You can think about it this way. The identification argument is that if we have infinite data set, if we have a huge data set, okay? If we have the entire population of these variables, then I can absolutely calculate this. That's called identification. Now, so in this case, we say this causal effect is 100%, is completely identified. If we observe F, W, C, Y. If we observe these variables, if we observe their entire population, okay, entire population, infinite data, if we observe them, then I will be able to uniquely calculate this, determine this. In this case, we say it is identified. Or I can also say it's non-parametrically identified, meaning I'm not assuming any parametric model. Am I assuming any parametric model for expectation, for this thing? No. Okay. Am I assuming any parametric model for this probability? No. I'm not saying this is a normal distribution. If I say this has to be a normal distribution in order for us to calculate this causal effect, then it is called parametrically identified, not non-parametrically identified. Here I'm not putting any assumption on these things. So it's non-parametrically identified. Now, in what case is it not identified? In what case is it not identified? Well, if I tell you that I actually do not observe C, and I do not observe W, and actually let me just say I do not observe F. So the only variable you observe is Y, but I observe infinite Y. Okay, I observe the entire distribution of Y, the entire population Y. Can you calculate this? No way, right? No way. In this case, we say the causal effect is non-identified. It's not identified. So that is the identification argument. Okay? All right. Now let's put them back in. Okay? Let me assume I observe F, I observe W, I observe C, I observe Y. So I observe all of them, and I observe infinite of them. Okay? So in this case, we are identified. Now let me say I observe all these variables. It's identified, but how do I estimate it? That's the second stage. The first stage is identification. Right? The second stage is estimation. How do I estimate it? Well, in order to estimate it, I have to estimate. This is the most important. Okay? This is less important. So let's talk about this one because I have to estimate this thing. What is this thing? This is E Y given conditional on F W C. Okay, right? So in order to estimate it, I need to find an estimate. Okay, because the expectation is the underlying population function. Right? It's a function on the underlying population. It's a CEF, the conditional expectation function in the underlying population. If I just see some data points, okay, so now I only see some data points. I do not see the entire population. From a limited sample, can you estimate this thing? If you want to estimate this thing, how do you estimate this thing? So how do you estimate this? How? Let me suggest. Let's suppose I'm going to make a drawing. I'm going to put Y here, and on this axis, I'm just going to put all the combination of FWC. Okay, so you can just imagine, right? Imagine this is all the combination of FWC, and then I see all these data points. How do I estimate EY given FWC? How do I do that? Well, what can I do? Well, I can do many things. For example, the easiest thing I can do is I can at every location I can do a neighborhood averaging that give me the EY given FC, a location that give me EY given C. But if I do not have enough data, then I may have to use a parametric model, which is a linear regression. But if the linear regression doesn't fit very well, let's try polynomial, and then we can do random forest, create a neural network, right? That's exactly the part we have talked about in the first half of our class. Okay? So in order to estimate EY given FWC from data, we can do anything statistical models. We can use any statistical models we have learned so far in our course. The simplest thing to do in traditional econometrics, what is the model that statistical model people use in standard econometric textbook? They say this equal to what? Equal to beta 0 plus beta 1f plus beta 2w plus beta 3c, right? And that's your standard econometric model, okay? Right? But of course you don't have to do that. You can use a random forest with variables FWC to predict y. You can use anything. You can use anything we haven't learned so far, neural network, right? Use it to predict y. It's all good. Okay, it's all good. Because now the task is not, because now we have already done the causal inference. We have already done our causal reasoning. Whatever left is a pure statistical task, which is how to use FWC to predict the mean value of y, condition model. Okay? So how to predict or how to use a statistical model to describe this conditional mean. So now is, you just find your best model. Okay? Find the best statistical model. It's a pure statistical thing, no longer causal, because we have already done the causal part. So in some, right? So in basically the idea is causal inference is two-stage. The first stage is pure causal reasoning that based on the graph, based on our causal graph, using pure reasoning to express the causal in terms of statistical, because this is pure statistical. This is causal. So the first stage is to express the causal in terms of statistical objects, which we can estimate from data. The second stage is to actually pick a model, a statistical model, to actually estimate the statistical object. Okay? So first stage, translate causal object into statistical object. That's the first stage, causal inference. The second stage of causal inference is to estimate the statistical object using any model that's fitting. Okay, that fits, that best fits. All right. So there you go. Okay, so that's the general picture. Now, so this is this case become easy. This case seems to be have solved, right? It's an easy case. What if? Okay. Now the question is, what if I do not observe W or C? What if I, right? So, okay, in this case, in order to know the causal effect of F on Y, using this formula, we need to control for the parents of F, which is W and C. What if I actually do not observe W or C? Can I still identify the causal effect of F on Y? The answer is maybe, maybe not. Okay? If we observe all the parents of the treatment, and the outcome, then yes, then you can always non-parametrically identify the causal effect. But what if we do not observe all the parents? Can you still non-parametrically identify the causal effect? The answer is maybe, maybe not. What is the criteria? We have two criteria to decide. The first criteria is called the backdoor criteria. The second is called the front door. Okay? So we have two front door and backdoor criteria that will help us decide when we do not fully observe the parents of the treatment, what can we do in order to identify the causal effect? The backdoor criteria we already talked about last time, but let me remind you what the backdoor criteria is. Actually, you can read the slide yourself, but let me go back to this graph. The backdoor criteria is very easy. The backdoor criteria says we do not need to observe all the parents in order to identify the causal effect of F on Y. We only need to observe some of them. What are these some of them? These are the variables that can block the backdoor path. What is a backdoor path? A backdoor path is any path between F and Y that has an arrow that goes into F. In other words, any path that is not this path, okay? Right? Because this is something we want, right? This is something we want. This is the actual causal effect. So any path, any open path that is not this direct causal path, we need to block it if it's open. So in this case, this path is not open, right? This path is open. So all we need to do is to block this path, okay? So in order to block this path, all we need to do is condition on W. So remember, F has two parents, W and C. The backdoor criteria says we don't need to worry about C. C could be unobserved. So we don't have to observe C, okay? All we need is to observe this W, because this W is needed to block this backdoor path. And once we choose the W, then we are done. Okay, then we are done. Okay, then we are done. So W in this case is a variable that we say in this picture we say W satisfies the backdoor criteria. Okay, right? The W satisfies the backdoor criteria. Now it turns out that if you as long as you condition on W, we can identify the effect of F on Y. I will show you the formula, right? But after you condition on W, can you also condition on other things? Can you condition? Can I condition on C as well? Of course, it doesn't matter, okay? Because you can condition on C and still is satisfied because the backdoor is all blocked, okay? Every backdoor blocked. But can you condition on P? Can I condition on W and P? No, because that opens the path. Can I condition on W? So W satisfies backdoor criteria. WP do not satisfy the backdoor criteria. Because if I condition on WP, then at least one path is open, right? Is open. So that does not satisfy the backdoor criteria. What about WCP? Oh, by the way, so WC is also satisfied, okay? So WC satisfies backdoor criteria. W satisfies backdoor criteria. WP do not satisfy. What about WCP? Does WCP, if I condition all three variables, does it satisfy the backdoor criteria? Yes. Because condition on P opens it, but if the condition on C, again, it's blocked, okay? It's blocked. So again, it satisfies the backdoor criteria. What about WE? Does it satisfy the backdoor criteria? If I condition on these two. Okay. Now, first of all, let's forget about backdoor criteria. If I condition on these two, can I get a causal effect? No, because this is actually what we want, right? Okay. So you should not condition on C. So it turns out that backdoor criteria actually has two parts. The first part says we must block all the backdoors. The second criteria says that the variable that you condition on cannot be a descendant of the x. Okay? Cannot be a descendant. So this is descendant because this is children. So the backdoor criteria says you cannot condition on this one. Okay? Because this is actually causal effect. No, you should not condition, right? So again, so WE also do not satisfy the backdoor criteria. Okay. So then that gives us this formula. Now in my slides, in order to differentiate all the different kind of variables, I'm saying, okay, suppose we have a variable, we have a set of variables, because it may not be just one variable, it can be many variables. If we have a set of variables called SV, meaning the set of variables satisfy the backdoor criteria, but the SV may not be a very good word, so I'm just going to call it Z, okay? So suppose there's a variable set of Z that satisfies the backdoor criteria, then there are two results, okay? The first result is Py given do x, let me say equal to 1, but you understand. Py given do x, Z condition on the backdoor criteria, condition on the variable that satisfy the backdoor criteria, will just be equal to Py given x. Okay? So that's the first result. So this result says, once you control on Z, condition on Z, control for Z or condition on Z, Z is the set of variable that satisfies the backdoor criteria. Then causation becomes correlation. Causation becomes correlation. That's the first result. The second result is what about P given do x? What about this? I just want to know. I don't want to have this. Okay, I just want to have Py given x. What is it? Well, Py given x. Py given do x okay? Right? You see that? Okay? So do x is just add a conditioning variable z and an integral with respect to z. Okay? So that gives you the overall of Py given x, right? But what is this thing? What is Py given to xz? Py given to xz is equal to Py given xz, right? Because according to the first one. Okay? According to the right? Okay? Get it? So in other words, the overall causal effect of x on y, not conditionality, the overall causal effect of x on y is equal to Py given xz integrated with respect to z. People get it? Okay? There's actually an easy way to write it, which is simply the expectation of Py given xz, but the expectation is taken over z, okay? with respect to z, right? It says the same thing as written this way, okay? So it's just PE, with respect to z. Okay. So that's the result of backdoor. So the backdoor criteria says, once you find a variable z, a set of variable z that satisfy the backdoor criteria, then your causal effect of py given to x will just be, okay, the py given xz, but just integrate with respect to z, right? And that's it. That's it. What if I'm interested in not p? What if I'm just interested in e? Okay, I just want to know ey given to x, or I just want to know ey given to xe. It's the same thing. Ey given to xe is just ey given xe, and ey given to x is just replace this p with the e. Okay, and just replace it with e, and that's it. If you want to multiply. Okay. Right. So let's try. All right. Let's try. Let's again try the try this case. Let's come back to this one, right? So according to the backdoor criteria, all I need is to observe the w. Right? W is the minimum. Like I said, there are many things satisfy backdoor criteria. Many sets of variables. W satisfy it. WC satisfied. WCP satisfied, right? Because you can continue, but W is the smallest minimum set of variables that satisfy the backdoor criteria. So let's say we observe W. What does this formula tell us? It tells us that okay, so I want to know, let me just write E here, okay? So I want to know E, Y output or yield given fumigation equal to 1. What is that? That is simply equal to E. First of all, the backdoor criteria tell me that conditioning on W block all the backdoor path. So the first thing we can write is this, okay, Ey given to f equal to 1 W is equal to Ey f equal to 1 W, right? Okay. First thing. The second thing it tells me is if I just want to write Ey given to f equal to 1, what is that? What is this? It is E y given x equal to 1 W, but integrate with respect to W. So PW, but I can just use summation. It's the same thing, right? Okay, same thing. Suppose W is discrete, then I use summation. Right? Okay, summation W. Right? Do people get it? You get it. Right? Okay. So I hope people get it. Okay. Right. So that's it. So two more things I want to say. So according to our formula here, Ey given to x is equal to, let me still write P here, but Py given xz, z satisfy the backdoor criteria, Pz dz, okay? So if z satisfy backdoor criteria, this is our formula. But what is this? What is Py given x? So this is causal, but what is correlation? What's correlation between x and y? Py given x. Is it also equal to this? Is this expression also equal to Py given x? If not, what is Py given x? Py given x is, well, I can also write it as what? I can also write Py given x as Py given x z p, is it pz? Is it pz dz? If it's the same, then Py given x is always going to be equal to Py given x. What's wrong here? Right? This is the formula when we have a z that satisfies the backdoor. But is it actually equal to p arguments? So this is a test of your knowledge of probability distributions and all that, right? Okay. How do you calculate distributions? The answer is very simple. This is not equal to this. Why? Because the correct way to write it, we can always write py given x is equal to py given xz, but this is not pz. This is pz condition on x. Okay? All right, so this is the correct formula, right? Because everything needs to condition on x. Everything needs to condition on x because we are conditioned on x, okay? We are conditioned on x. So, this is correlation. This is causation. All right? This is causation. This is correlation. They're different. In what case are they the same? When z and x are what? Independent. So when z and x are independent, they are the same. All right? If z has nothing to do with x. So very good. All right. Okay. All right. So back to this graph. So let's see. According to this graph, I can write these two formula. And so what does these two formula tell me? So according to this graph, I say W satisfies the backdoor criteria. And from that, I can write these two. So what does these two actually say? These two, first of all, what I'm doing here is still identification argument. I'm not doing estimation. Estimation is how to estimate these statistical objects from data. Identification is how to transform causal objects into statistical objects. So right now what I'm doing is still transforming causal objects into statistical objects. So this is still identification. But what kind of identification am I saying? Here I'm saying that the causal effect of f on y is identified if we observe fy. Of course fy, right? So you want to do the causal effect of f on y, you have to observe fy. But it's saying that in addition to fy, if we observe which variable? Which variable? W, okay? So the identification argument here is if in addition to fy, if we also observe w, then this causal effect is identified. Why is it identified? Because we can express the causal effect in terms of the statistical objects which we can estimate from data. All right? If w is not observed, then there's no way for us to get this from data. There's no way. In this case, the causal effect is not identified using this strategy. Okay? So that's what I'm saying. So, in summary, remember previously. Okay, hold on. Right? In summary, remember this formula? This formula is our original broad formula. Okay, it's general formula. So this formula says the causal effect. You can calculate the causal effect if we control for all the parents of the treatment. Okay, using this strategy, we say, look, we say if I observe W and C, because these are the parents of F, if I observe W and C, then the causal effect of F on Y is identified. That's our previous result. Now, I'm using backdoor criteria. Using backdoor criteria, it's what the backdoor criteria says is you don't need C. Okay, we don't need to observe C. If we observe W alone, then the causal effect is identified. That's what the backdoor criteria say. So now here the question is, what if the W is also not satisfied, observed? If we do not observe W, is there any way for us to identify the causal effect of F on Y? So here, right, people follow the logic. The logic is we begin with a statement that if all the parents of the treatment is observed, then we can identify. Then we say, what if we don't observe them? What can we do? Well, the backdoor criteria says, yeah, you don't need to observe all of them. Just observe the W. And then we can identify. But what if the W is also not that, right? So we don't want to see this, we don't see this. Can we still observe the causal effect? Identify the causal effect? Well, the answer is yes, we can if we observe E, okay? So if we do not observe F, W, we don't see if we observe E, yes, then we can. And using something called, as you can guess, yes, called the frontal criteria, okay? So the frontal criteria says if we can establish an isolated and exhaustive mechanism from X to Y, then we can identify it. What do we mean by is isolated and exhaustive? It means, look, let's take a look at this one, okay? So X goes to M, M goes to Y, and there's a U. Now, if we can find a path, like the path between, I'm sorry, the path from X to Y, okay? Now, if we can find a path like this, which is exhaustive, means that's the only way, okay? The only way to go from X to Y is to go through some variable called M. M is the only variable. The only way to go from X to Y is to throw M. Okay, is to throw M. So M is a variable that, if we observe, can help us get the causal effect of X on Y, even if we do not see U. Remember, if we do not see U, right? If we see U, right? If we observe U, what can we do? We just need to condition on U, and then that blocks the backdoor path, right? In that case, we get the causal effect. Okay, we identify causal effect. So if we observe U, we are done. We use the backdoor criteria to block it. Block it, condition on U, we get the causal effect. But if we do not see the U, it's unobserved, then we need to see the N. Because N can also help us identify the causal effect. How? Let's do it, okay? Let's see. Let's try. Let's take a look at the example, okay? U, F, X, M, X, M, Y, U. Now I'm going to assume that I do not observe U. I only observe N, N, X, and Y. How do we get a causal effect? Well, let's think about it. What is P? So I want to know Py given to. I want to know Py given to X. Okay. What is Py given to X? Well, let me decompose it. Let me decompose this into Py given to M. Okay? And then Pm given to X. Can I do that? The causal effect of X on Y is the causal effect of X on M and the causal effect of X M on Y. Can I write that? Yes or no? Yes. Why? Why? Because the only way for we to go from X to Y causally is through M. So the causal effect of X on Y will be the causal effect on this and this on that, right? Has to, okay? Has to, because this is the only way we go from X to Y, all right? Now, if we want to write it more clearly, let's suppose M has many variables, okay? M can be 1, 2, 3, etc., okay? So then it's really the probability Y given do M equal to a small m, a value, okay? And the probability that M equal to small m do X, and we need to summation with regard to M. That's it, okay? So that's a complete way to write it. Okay, so this is all we can always write that because M is in the middle of X and Y. Now let's take a look. What is this thing? First of all, what is this is easy. Okay, this is easier. What is Pm given to X? From this part, what is Pm given to X? Can you write it in terms of statistical object? Pm to X is a causal one, right? Can we write it in terms of statistical one? Yeah, very good. It's just Pm given X, right? Right? M equal to small m given X. It's just that. Pm given X. Why? Because it's direct, right? There's no other things, okay? There's no backdoor, right? There's no any backdoor path, open path from X to M. There's only this link. So Pm given to X is Pm given X. That's very easy. So that's part is done. Okay, we get it from data. What is this? What is py given to m? Is py given to m? Is this equal to py given m? Is it? Is py given to m equal to py given m? Why? Because there is a backdoor path, right? So how do we condition on what? We do not see this view, okay? U is unobserved. So what do? We condition on x. Because condition x block the backdoor criteria, right? Backdoor path. So what is this equal to? This is equal to py given m, right? Given m equal to m, but also given what? Condition on x and px, right? And that, right? Okay? And just take it and just, just summation over x value. This is equal to this, right? Okay? So this is equal to this. So finally our formula is, that's it, okay? That's it. That's our final formula. And by doing this, I'm expressing the causal in terms of everything is statistical. The causal is expressed completely in terms of statistical objects, which every one of them can be observed, is observed and can be estimated from data. Right. So guys, what I'm saying here is once we observe m, right? Observe this m, and we can get the causal effect out. So the causal effect of x on y is identified if we observe m in this case, even if we do not observe u. So m is in this case m is said to satisfy the front door criteria. Now people can see why it's called front door, why it's called back door. Do people see that? This is the back door, right? Right? This is the front door, right? The front door is, if we want to go from x to y, you can go through the front door or you can go through the back door. So we can either block the back door or we can use this mechanism to adjust for the front door, right? So that's why this is called front door criteria, the other called the back door criteria. Okay? Right. Now, if we do not use front door, back door, these kind of names, then you can say that the backdoor criteria is actually equivalent to, basically amounts to controlling for the confounders, and the front door is equivalent to just exhaustively go through each mechanism directly, okay? Just estimate each mechanism directly. All right. So let me summarize, okay? What is, we say m, okay, we say any variable, a variable satisfies the front door criteria if, first of all, condition on this variable block all the path from x to y. That's the first condition. So this m satisfies the front door criteria if, that's the first condition. The first condition is condition on m block every path from x to y. So this criteria is basically saying that m has to lie on each causal path. Okay? M has to lie on each causal path. So condition on m block all the causal path. This is the causal path. This is not a causal path. A causal path means, from x goes to y. Okay, from x to y. So that's the first condition. The second condition is no open backdoor path exists from x to this variable. What do we mean? From x to this variable, m, okay, from x to m, there is no open backdoor path. No open backdoor, only direct path, okay? No open backdoor path. Why do we need this condition? Because we want to say m given to x is basically m given x. Okay? In order for this to be true, m given to x equal to pmx, there should be no open backdoor path. Because if there's open backdoor path, then the causal effect of x on m is no longer the correlation between x and m. Okay? So the second condition is no open backdoor path between x and this variable. But then there's the third condition is condition on x block all the backdoor path from this variable to y. Okay? So this is a little bit, right? Now it's only making intuitive. The third condition is condition on x we can block all the backdoor path from M to Y. This is what enables us to do this step, okay? To do this step. So if we can find a variable that satisfies these three conditions, then we say this variable satisfies the front door criteria. Okay? In summary, a front door criteria, the variable that satisfies the front door criteria are the variable, first of all, it lies between x and y. Okay? So basically every time we go from x to y, we have to go through this variable. Causally, causally. First condition. Second condition, no backdoor path between these terms, okay? No open backdoor path between them. Third condition, condition on x, no other open backdoor path from here to here. So that we just need to condition x and we're done. Okay? So that's the front door criteria. Alright. Okay, now let's go back to this basic graph, right? So in this graph, what is the variable that satisfies the front door criteria? E, okay? E satisfied. Why does it satisfy? First of all, the only path goes through E. Second, there's no open backdoor path. There's no backdoor path between F and E. Third, there is a backdoor path from E to Y. Okay, there's a backdoor path from E to Y, but this backdoor path is blocked by F. So E satisfies all three conditions. So E satisfies the front door criteria. So in other words, if we want to identify, so condition on E, if we observe E, then we can also identify the causal effect of F on Y. All right. So summary, okay, summary. We begin by saying, if you observe all the parents of treatment, identified, okay, causal effect identified. Then we say the backdoor criteria says we don't need to observe all the parents. Just observe the variable that block all the backdoor path, then the causal effect is identified. Then the front door criteria says you don't even need to observe W. Okay? If you do not observe W, you do not observe C. But if you observe E, it's also identified. So in summary, finally, we arrive at the conclusion that at least for this graph, either we observe W or we observe E. In each case, the causal effect will be non-parametrically identified. Okay? So that's our final conclusion. You have a question? Yeah.
So this means it wouldn't work if we had another thing like another mediator just on a line between F and X, Y.
Can you, so let me draw it, because I'm not sure graphically what your question is. So we have a W, we go to F, F goes to E, E goes to Y. So what is your question? You said if there's another mediator?
Yeah, just have like the same graph, but have another line like the one from F to, but also having also another variable inside. We say there's two.
So let me name this variable A. So what's your question?
If the front door criteria can still work, because we have to use 2 then, or?
In this case, the front door criteria says if you observe both, if we observe E and observe A, then we can use the front door strategy. But if you only observe E without observing this A, then you cannot. Okay.
So we always have to observe all possible mediators.
For the front door strategy, yes. So that's why in the front door criteria, there is an important word which is exhaustive. So we have to have an exhaustive mechanism. So meaning that we have to observe all the mechanism, okay, all the mediators in all the mechanism, and then we can do it. Otherwise, you cannot do that. All right. Okay. We still have some time. Now let's go to the next topic, right? What if? Okay, what if? So here's a what if. What if I also do not see M? Right, so causal inference the difficulty for causal inference is not, as you can see, the difficulty for causal inference is really the difficulty that we do not see everything, right? Because if we see, right? Okay, so hope you get it. The difficulty with causal inference is that now if we observe all the variables, then there's no difficulty with causal inference. Just use the adjustment formula, control for the parents, and you are done. Okay? No difficulty. at least no difficulty with identification. If your data point is not enough, you have some difficulty with estimation, but no difficulty with identification. So if we see everything, identification is done. But what if you don't? What if you do not see the parents? Well, if you see W, we can do this. If not, if you see the E, we can do this, right? So causal inference, the difficulty of causal inference comes from the difficulty that we do not see everything. We only see part of the graph. So now what I'm going to say is, what if I do not see C? I do not want. Actually, let me just say, what if I do not see W, and I do not see E? I don't see W, and I don't see E. If I don't see W, well, give up is a very good strategy, right? So if I don't see W, no backdoor criteria can use. If I don't see E, no frontal criteria can be used. So we can give up. If I do not give up, is any other way to do it? Okay. Now it turns out that if we do not see W, then backdoor criteria is not satisfied. If we do not see E, the frontal is not satisfied. But we can still find the causal effect if we're willing to do parametric identification. What do I mean by that? Before talking about what parametric identification is, let me just say that backdoor criteria and the frontal criteria are criteria for non-parametric identification. What is non-parametric identification? The non-parametric identification says our causal effect we're interested in can be expressed as statistical objects without putting any parametric assumption on those statistical objects. Okay? So that's called, it's non-parametric in that case. Non-parametric means no parametric assumption. So this P can be anything. This P can be anything. It doesn't have to be normal distribution. It doesn't have to be a linear function, right? It doesn't have to be anything. But if we have to put a parametric assumption on these guys in order to achieve identification, then it is called a parametric identification. But in saying so, we should always be careful, because when we estimate things, we can also have parametric estimation and non-parametric estimation. What do I mean? Well, let's go to right. So let me just let EY given do x equal to 1. Suppose I say this log, this is simply equal to EY given do x equal to 1, x equal to 1 W, right? So W set is a backdoor criteria, PW, okay? All right, so I can write it this way, if W satisfy backdoor. Now, this is called non-parametric identification, because I have successfully written the causal object in terms of the statistical object without putting any parametric assumption on them. So it's non-parametrically identified. It's non-par identified. However, how do I estimate this? Remember, identification is the first stage. Estimation is the second stage. How do I estimate this? Well, I can estimate this thing non-parametrically using the nearest neighbor, right? Okay? Right, so yx, just take the nearest neighbor and estimate this thing. So in this case, we say it's non-parametrically identified and non-parametrically estimated. Okay, because we're using neighborhood, KNN or whatever neighborhood to estimate this thing. However, I can also parametrically estimate. I can say this is simply a linear regression. This is equal to beta 0 plus beta 1 x plus beta 2 w. So if I do this, then we say it's not parametrically identified, but it's parametrically estimated. Right? Okay? Because I'm using a linear function to estimate it. So identification and estimation are separate things. Okay. So let me come back to this topic. Okay. Now, if I do not observe U, and if I do not observe M, then backdoor and the front door both fail. So we cannot non-parametrically identify. So let's try some new method, okay? This new method is here, which I believe all of you are very familiar with, okay? What is it? What is it called? It's for the instrumental variable, so IV. Okay. So the IV setup is this: I have x, I have a u, I have a y. There is a u that goes to x, goes to y. There's something called I here, right? Something called I here. Now the u is unobserved. If u is unobserved, the causal effect of x on y is non-parametric, is not non-parametric identified. There's nothing you can do because there's an open backdoor between them. However, if we observe an instrumental variable, if we observe a variable that goes to x, okay, actually, let me just, if we observe a variable that the only way for this variable to go to y is through x. The only way for this variable to influence y is going through x. If we observe this thing, and this variable is also independent from the u. If we observe that, then we can use it as instrumental variable. And if we are willing to put some parametric assumption on what this graph, what the function governing this graph looks like, then we're able to get the causal effect. So let me give you the detail, right? So basically, but you are familiar with instrumental variable. So all I'm doing here is to put instrumental variable in terms of graph language. So we can, you are familiar with how the assumptions that you are taught in econometrics translate into graph terms, right? Okay. So first of all, in graph terms, what variable satisfy the requirement of instrumental variable? Now, in traditional econometrics, the way you are taught is that somebody tell me what is instrumental? What condition do we need to set? Yeah, but what exogenous mean? What is it correlated with? Is it not correlated? It's correlated with what? It's not correlated with what? Like what? It's correlated with x, but not correlated with what? It's not correlated with what? It's not correlated with error, right? Okay, all right. So let's talk about a graph term, right? In graph term, we say a variable can serve as an instrumental variable if it satisfies two conditions. The first condition is this variable is associated, is correlated with x. Okay? Same thing, right? Correlated with x. Now, let's take a look at this one. Is it correlated with x? Yes. But it doesn't have to be this, okay? I can also have this. So this is I. This is I. This is x. Y. This is u. Goes to x. Goes to y. Now it doesn't have to be like this. I can also have maybe let's call it v. This v is also unobserved, but v goes to I. V goes to x. I can also do this, right? Because in this case, this I is also correlated with x. Okay? So the first condition is it's actually correlated with x. The second condition is every path, okay, every open path connecting the instrumental variable to y has an arrow pointing into it. So every path that we want to go from I to y, okay, every path, every open path, if it's blocked, forget about it. So every open path from I to y has to go into x. Has to have an arrow into x. So that's basically the graph translation of the language I just used at the beginning, which is any way that I influence y has to go to x. Okay? Same thing, the same thing. So in graph terms, it just means every path has to go to x and it has to have a point into x. Now, but how does that relate to the condition intercept? The intercept, in the dimension class we were taught that something has is the instrumental variable two conditions. First condition, if I and x are correlated, okay, the correlation is not equal to 0, which we already see here, right? The second is the instrumental variable and the error term. The error term is not equal to 0. Now in this case, by the way, what is the error term? If you, in linear model, if you write y equal to beta x plus error term, right? What is this error term in this graph? The u, right? Right? Because y is determined by x, and e in your linear model, the e is the u, right? Because y is determined, because y may be, right? Because we want to know the causal effect, right? So y may be determined by x, That's the causal effect we want to know. But y is also determined by u. So this e is the u, right? This e is u. So the second condition you have is instrumental variable and this error term correlation is equal to 0. Okay, is equal to 0, which means the I in the graph term means the I and the U has to be independent. Are they independent? Why? Because X is a collider. Now, because remember the condition I gave here doesn't say they have to be independent. The condition says instrumental variable is correlated with X, and every path from instrumental variable to Y has to have an arrow that goes into X. Now it turns out that this condition, have to have an arrow goes into X, is what guarantees that I and the U are independent. Why? If U also causes X, that X will be a collider, because we make sure that the path goes into X, right? The arrow goes into X. So if U also goes into X, then the X will be a collider, so they have to be independent. If U does not cause X, then of course they are independent, okay? So in any case, this and this will be independent. Right, so that's essentially the same condition, right? The same condition. We're just using the graph terms to translate something that we talk about in econometrics. Okay? All right. Now, okay. So now we're saying, but this is not enough. If we simply have a variable, instrumental variable that satisfies the condition, we still cannot get the causal effect out. We still have to put some parametric assumption. Okay? We still have to put some parametric assumption. It's not non-parametric identified. What is the parametric assumption we need to put on it? Well, you can put many, but let me just put a very simple one. Okay? Extremely simple one. I'm going to assume y is linear in x and linear in u. So I'm going to say y is actually equal to beta x and alpha u. Okay? So y is a linear combination of x and u. This is a parametric assumption on the causal graph. Okay? Now, with this parametric assumption on the causal graph, we are able to get, we are able to get the causal effect out. So in this case, the causal effect is parametrically identified. It's now non-parametric identified. So, okay, all right. So how do I get, so once I assume this, how do I get the causal effect out? Then it's very, very simple. You're all familiar with, okay? If I assume this, then what is the covariance between y and the instrumental variable? You know, it's all familiar. You've heard this in many times. It's basically the covariance between y is this, y is beta x plus alpha u with the instrumental variable. But we know that instrumental variable is I and this u are independent because this x is a collider. So this part is gone. Okay, this part is gone. So the only thing left is covariance between x and I beta, right? Beta. Now this beta, right? So okay. So in other words, the beta is, the beta is the covariance of yi divided by the covariance of xi, and this beta is our causal effect because we are interested in causal effect x or y. And if I make this parametric assumption, then this beta is the causal effect, right? So the causal effect can be we can immediately get the causal effect from what? From this, okay? From this, right? But it's only true if we can make some parametric assumption. It doesn't have to be linear. We can make a nonlinear assumption, but it has to be some parametric assumption on this relationship. Then we can get our desired causal effect using the instrumental variable strategy. And so in this case, we say instrumental variable helps us to parametrically identify the causal effect. Okay, parametrically identify. Okay, so we're running out of time, but let's go back to the fumigation example. Right? So everything revolves around this. So okay, now if we observe W, we use the backdoor criteria. If we use the if we observe E, we can use the front door. If we do not observe W or E, any way for us to get the causal effect of f on y? Any way? Let's say we do not observe W, do not observe E. What can we do? Right? What is the C? It's C satisfy what condition? C is what? C is our instrumental variable, right? People see that? No? People do not see that? The C satisfy instrumental variable sort of criteria? Remember, criteria for instrumental variable. First criteria has to correlate with our treatment, right? The treatment is F. We're interested in causal effect of F on Y. So C is correlated with F. Second condition, in order, every path from C to Y that is open, okay? We don't care about blocked. Every open path from C to Y go through F, right? And has an arrow pointing into F, correct? We go through F. So C has two paths to Y. There's two paths from C to Y. One path is here, but this path is blocked. The other path, there are actually three paths, right? One path here, sorry. One path here, the other path is here, right? But these two paths both go through F as arrow pointing to F, correct? Okay? So, question, is C, first of all, C and F are of course correlated. Now, is C and Y is determined by, what is Y determined? Y is determined by, forget about the E, right? E is not, Y is determined by F and Y is determined by W directly. We do not see this W. That's a problem, right? That's why we cannot use backdoor. So, this W is like our E, right? It's like a U, correct? The unobserved thing. Is C independent from W? Is it? It's independent, right? Because every path from C to W is blocked. Okay, blocked here, here blocked by F. Okay, so C is independent from W. In other words, so let's just make the assumption. Let's make assumption that Y. Okay, so in other words, the correlation. So the in other words, C is independent from W, and C is correlated with F. So Y is determined by F and W. So the correlation between Y and F, or the covariance between Y and F, right, can be written as the covariance between the combination of W, right? So if we are willing to write, so let me write Y equal to beta F plus alpha W. I can always do so, right? Because Y is the effect of F, and Y is the effect of W, right? I can always write that. And then what is the covariance between Y and C? What is that? The covariance between Y and C is the covariance between this and this with C, but C is independent with W. So in the end, this is beta covariance F and C, right? So these two divided give you the W. Give you the beta, which is the causal effect. Okay? So in other words, if I observe C, but I do not observe E and W, then I'm also done using the instrumental variable strategy. The only sacrifice here is I have to be willing to make some parametric assumption on the function of Y. On Y is a function of W and F, right? I have to make some parametric assumption here. If I'm willing to make that, then I can use this strategy to back out the typically a linear assumption, but you can, it turns out that you can also use, but using linear assumptions is often the easiest way that you can do to back out the causal effect directly using the instrumental variable. Right, so we don't have time, but let me just summarize. Right? In summary, observe W and C, we're done. But if we only observe W using backdoor, if we do not observe observe E using frontal, if we do not observe W or E using C, right, as an instrumental variable, and we can get out the causal effect. Okay, so let's stop today and continue next Tuesday.